And I will share my screen. How do I share my? How do I share my screen? Can't even get this right.
There is a green button at the bottom of the Zoom.
Got it.
Yeah.
Okay, don't know which screen that is sharing. Can you see my slides there?
It says it's still sharing, started screen sharing, but not appearing yet.
Just a minute.
Yeah,
Oh, it's
now
got
I see
now.
it.
So you can see my slides?
Yeah.
Good, good, good. Okay, lovely. Right, off we go. So, chapter 6, the introduction to machine learning. Now I've broken this chapter into two halves because it's quite a big chapter. It's important to get it right, and I think for myself as well, there are some concepts I'm familiar with and other things that are a little bit new to me. So I wanted to make sure that I did the chapter justice and that I was explaining clearly and everybody could follow along in a reasonable way. So we're going to go up to section 6.3.1, if you've had a chance to look at it, which includes the cholera example. So the main learning objectives for this chapter are to have a look at the basics of how to construct a machine learning model and to start having a look at how you might apply different techniques, starting with basic techniques and then working up to machine learning, which will be covered in the next section in more detail after the break. So we've got a break of about 3 weeks. So we're going to review an example of modeling a fast-growing phenomenon. So there are kind of two sort of approaches you can use in general. A stochastic model uses probabilities that replicates uncertain outcomes and random behavior, whereas a deterministic model will model the spread of a virus, for example, under certain conditions, such as a fixed number of individuals or contagiousness, but doesn't account for randomness or the kind of uncertainty that you might see in reality. So we're going to be having a look at the susceptible infected recovered model, or the SIR model, which is a deterministic model, so you get a good idea of what that is. And it describes the dynamics of the spread of a virus, but can also include stochastic elements, such as the random interactions between individuals. We start off with a basic example, but they can be more complicated. So machine learning really is considered a subfield of AI. It differs from conventional statistical models that you might be familiar with from previous training, if you've done any kind of statistical courses, in the way that the parameters are calculated and calibrated. So with conventional models, you need to understand your variables, your potential relationships between them, and you will then build a robust model that's capable of making reliable inferences about your data and about the relationships. Whereas machine learning models are said to learn from data and will automatically adjust parameters to find the best fit or the optimal fit. And the diagram that I've produced here, which is described in the chapter, it's not prescriptive. It's just to give you an example of where you might start with data collection and the steps that you will go through: data pre-processing, cleaning and filtering, and making sure that you have a good data set for the case, for the question that you're trying to answer. You've got rid of duplicates, things like that. And then you'll go through steps to select your model, to train your model on a portion of your data, and how to evaluate your model. And you can go back and repeat steps along the way in an iterative process to refine your model and improve it before you finally come to a point where you might want to then deploy your model so that it can be used by other people. But we'll be coming back to this later on in this session. But it's not a prescriptive thing. It's not, oh, you have to get to this point and then go back. So you may need to repeat some of these steps. So there are empirically driven and mechanistic models, and to understand more about where machine learning might fit within these, in this sort of framework, we can look at a mechanistic model known as the SIR model that I mentioned. And it's a commonly used model that's used for the spread of infectious diseases to understand them. And it's also known as a compartmental model because it tends to compartmentalize populations into susceptible, infectious, recovered. There's an additional step that can be used in more complex models, exposed, SEIR. And what they have, there's a series based on a series of differential equations. If you're not familiar with differential equations, they're equations that are related to each other, and you can differentiate to find the answers. And it's from a branch of mathematics, calculus, which deals with rates of change. So you can look at this, for example, this is ds by dt. So it's the susceptibility at a given point in time, susceptible individuals, and how to calculate that. I, infectious people at a given point in time, and recovered at a given point in time. And I've found a really nice sort of analogy that's based on buckets from a presentation slide that I thought was quite helpful for me, at least, to understand a bit more about people in each of these compartments, susceptible, infectious, or recovered. And that sort of, it's a nice, useful thing to think about if you're not familiar with differential equations and how these things might relate to one another. So we're just looking quickly at an example of empirically driven models. So machine learning models are empirically driven, and what that means is that they derive patterns and relationships directly from data without the explicit knowledge of the underlying mechanisms of relationships. So with the SIR model, they rely on known relationships between variables and based on mathematical equations. But that doesn't mean that machine learning models don't have underlying mathematical principles, because they do, and they can be quite complicated. So I've just created a quick example here using the iris data that's built into R. Just having a look at the potential relationships between each of these three species based on measurements of petals and sepals, or floral parts. I'm a botanist and a horticulturist, so I love the iris data set. And I just applied a very, very simple, very quick random forest model. And the way a random forest model works is that it creates different numbers of trees. It works through the data and it calculates binary. So you can see this binary selection based on the sizes of petal widths and petal lengths and sepal widths to group species according to the lengths and widths of these attributes. And this is actually quite a good example because it does reflect the relationships between these species. If you look at a scatter plot, if you plotted any of these lengths and widths, you would find that this species does actually sit in a cluster on its own anyway, and there's a lot of overlap between versicolor and virginica. But I think what's good about a random forest is it will take all of those attributes, whereas in a scatter plot, you would just plot petal width against petal length. So it's quite reductive in that sense, whereas this does have a more holistic way of looking at species relationships and building these kinds of trees, which are quite common in phylogenetics. So the way machine learning models work, so you have supervised and unsupervised methods. With supervised learning, your data are labeled, which means that the data set shows or identifies both the independent predictor variables, your X variables, and the dependent or outcome variables, which is the Y variable. And that type of model predicts the outcome variable based on input variables. And there are machine learning models that are based on linear and logistic regression, for example. I've used some of these in a very applied sense. And there are also unsupervised approaches where you have the input variables, but there's no direct objective or a response variable to focus on. So the model learns to find patterns and relationships in the data without having explicit labels. And that kind of approach might be quite useful if you have a large number of variables, if it's quite complex, and if you want to find overall patterns or clusters, or if you want to reduce your dimensions in a robust way and create latent variables or construct variables from other different types that you have in your data. So the choices you make for picking a model or several models, if you want to try different approaches, depends on the type of data, the complexity of your data, and your research questions. And it also depends on whether your outcome variable is continuous or discrete, whether the number of predictors might exceed the number of observations. So the way the machine learning model learns from data is a process where an algorithm adjusts parameters to minimize the errors in prediction. And each algorithm has its own way of doing this. So what you want to find is with your observed variables and your predicted variables, you get an error, and you're trying to reduce that error as much as possible, which you would do in any kind of statistical modeling approach. So we're going to have a sort of look at parameters and hyperparameters. You might have heard these terms. You might be more familiar with machine learning than I am, but they're quite distinct concepts, and they're very, very important for building and tuning models. So in statistical modeling, parameters might be things like the intercept and the slope that can be optimized. And the purpose is to find the best fit for training data. Hyperparameters, on the other hand, are external settings of a model that can be redefined by you or optimized using different types of search techniques, or maybe more advanced approaches like Bayesian approaches to modeling. So examples of these might be the sample size or the number of trees you might have on a random forest model, like that we just looked at in the very simple example with the iris data. If you have a very large one, you can set the number of trees or limit it. And other hyperparameters might be the way the model learns, the rate at which it learns, and there could be other settings such as used in ridge and lasso regression, where you might have a case you've noticed some kind of multiple collinearity, or where two predictor variables are highly correlated to each other. So you don't get unique or independent information in the regression model. So it can cause the model to be unreliable and perform quite poorly. So when you're modeling any kind of infectious disease, it is important to understand underlying patterns and dynamics of growth. So you might want to carry out quite a lot of exploratory analysis just to get a better understanding of what your data looks like, how it feels, and what the variables are. And it can involve high-level calculations. So even though machine learning, it might sound like, oh, you just unleash a bunch of data onto a model, you do need to have a good understanding of what you're actually doing and how the model is actually working. And when you're studying infectious diseases, your focus is on how things might evolve over time. And selecting the appropriate model does require a good understanding of how viruses, how diseases change, and the dynamics of growth and how populations function. So having a look at the steps of building a model, I think that the chapter does contain this really nice diagram that I've reproduced that I sort of showed a version of earlier. So you kind of have your data collection process using robust techniques for collecting data to answer your research question. And then you will clean your data, looking at any missing values, removing outliers. You also want to be careful with looking for duplication, because that can cause a lot of problems in making inferences or predictions later on. And then you'll go through selecting relevant variables in your model, training your model on a subset of data and checking to make sure that it's doing what you might expect to see, looking at different algorithms and how they function. And then with the other part of data that you have in your data set, you will then apply your model to those data and see how they perform on a larger portion of that data. And then you might also want to test your model with a new set of data that it hasn't seen, and see how the predictions work, and how the model performs with those data. And then you can go back and optimize your model performance if things don't look right, and if everything checks out, you will then send it out into the world and see what happens. So it's quite an important step, model building, and it is really essential to get it right, because these kinds of things can be used to inform decision making and maybe even policy. So it is important to do it right. So I was just going to have a quick look at just an overview of where we're going to start with a model function where you have a response variable, which is y. In this case, the example could be the number of deaths or infections in a population, and then you have your function with your predictor variables x1 to however many you've got. And then you've got your error term, which is, as I've mentioned before, the difference between your observed and of your response variable and the ones predicted from the model, which you're trying to minimize through your model selection and refinement process. And the way machine learning works, depending on what you choose, it optimizes these coefficients so that you get the least error between them. And then once you've applied your model and you've evaluated it and you've gone through those steps, the function that you create here can be used on new values of X. As I mentioned, you might want to test it on a data set that it hasn't seen to predict any future values in the response variable. So having a look at the first example in the book, we're going to have a look at some R code, which is always the exciting bit. Having a look at cholera. And using the data set from the HIST data package, there are 730 observations, 6 variables, and it contains 2 causes of death. The other one being diarrhea, because it's quite, diarrhea is fatal in many parts of the world, and it has been in the UK in the past. But in this case, we're filtering on the cause of death, which is cholera, over a 12-month period from the 1st of January through the year in 1849, which is when we had a cholera epidemic. So the 2 variables we're selecting on are date and deaths. And to have a quick look at those, so the predictor variable is date from the 1st of January, 2nd of January, 1849, and the response is the number of deaths. And this is a count of the number of people who died. And just summarizing there, so the response, Y deaths, the predictor, X date, just a very simple model, nothing too complicated at this point. And we can have a look at what that looks like. So in the case of infectious diseases, and certainly in the case of cholera in London in 1849, the trend sort of starts at a certain point and then it goes up, it reaches a peak. Here it sort of trundles along from January, and about June it starts to rise, the deaths start to rise, it goes up, but it fluctuates a fair bit. And about September-ish, it reaches a peak before eventually going back to where it might have started in the very beginning. So you can see that it's really not a linear pattern. There's no direct linear relationship between X and Y. So how are we going to model this? Well, we can, I've just done a quick recap of linear equation, the equation of a line for people who may not be familiar with it. So this is generally the response variable. This is the intercept, or the point where your response crosses the Y axis when X is set to 0. And then beta sub 1 is where the average change in Y increases, each unit increase in response to a change in X, and X is the value of the predictor. So as I mentioned, there are kind of, in a normal model for something like this, you might have multiple predictors. In this case, we have one to keep it simple. So looking at two approaches, linear models and locally estimated scatter plot smoothing, to visualize what that might look like at different points in time on the cholera data. So a linear model assumes a linear relationship, which we've just looked at, the equation of a line. And we're filtering on a subset of time points from the 1st of June to the 1st of August, with on the x-axis, we have our predictor of date, and the y-axis, our response of deaths. And we can use the geom smooth function to set a kind of linear line across the points to see what that looks like. And here it is. And you can see from June to August, using a linear approach, there's a lot of wiggling of points around this straight line. So it's not a particularly good fit. Using a locally estimated scatter plot smoothing approach, which makes no underlying assumptions about the structure of the data and can fit a sort of a smoother line around your points. We can look at data from, the example is 1st of August, 1849, similar kind of parameters, but without the linear model function. And we can see that using more data points from earlier in the year, we have this curve, but there's still quite a lot of wiggling around this curved line where the infection really starts to spread and people are starting to die. So again, it can be useful for some situations, but it doesn't really adequately model these sorts of data. So we can compare linear, non-linear models. So if we can have a look at something known as generalized additive models. These, if you're not familiar, these are extensions of linear models that combine parametric and non-parametric techniques to model non-linear relationships. And the way they do that, so the non-parametric techniques, they use something known as splines or kernel functions. And I'm familiar with splines from, weirdly, garden design, because I trained in horticulture and we did garden design. And in engineering, it's an engineering concept. It's basically a flexible curve that you can bend if you need to draw curves between fixed points. And it's a similar kind of approach with generalized additive models, where you can have fixed points along a curve and it will calculate that curve and at different points in time and create a nice smooth line to fit your data better. So we can have a look at what that looks like. So here's the linear model, this straight line, which doesn't really work in the context of the data. And this red line, this wigglier line, is our generalized additive model. So kind of a little bit more about generalized additive models. So they can be used quite effectively. I've never actually had cause to use them myself, or maybe I did and I didn't know it, because it's not the kind of thing that gets taught generally on a stats course as part of another degree, unless you do a degree in statistics or something. So they can be used for modeling complex relationships between a response variable, deaths, a number of deaths, for example, and our predictors. Here we have one, which is date. And so your response variable, G of mu, will be the parametric, whereas these predictors, so this is again from the linear model, this is the intercept where the response intersects with the line when x is set to 0. And this is the function. And you can, if you have lots of predictors, you can nest each function for each predictor. So you can do it at an individual level for each predictor variable. And it's pretty good at capturing nonlinearity in complex patterns of data. And this is a link function that tends to be chosen based on the distributional characteristics of the response to represent the data mean trend. So we can have a look at fitting a model, and to do this in R, you can use the MGCV package. And instead of the full date, create a new variable, which is days based on the row number. We can have a look at that. So it's the same kind of data as before, but instead we now have days as an integer and an additional column. And to fit the model using a GAM function, so we have the response, which is deaths, and we apply a smoothing function to days on the data collar, a very simple model, and we can have a look at the output. So this describes information about the model that was used. So it's applied a function and picked a family because we haven't specified anything else, and the basic formula that we've applied. And you can see this is the response variable. It's a parametric coefficient. It's been modeled in a parametric way. And further down, the days, as specified in the model, have had a smoother, non-parametric. And it's significant based on the approximate significance test. The EDF is the effective degrees of freedom. Now I've just put some key points down here, more as an aid memoir for myself, because this is quite a new approach for me. So where your effective degrees of freedom are closer to 1, it implies that there's more of a linear relationship between variables. So the higher the number, the wigglier the line between your predictor and your response variable in this case. And so looking at the adjusted R-squared value, this particular model explains approximately 91.4% of the variation that we can see in Y. And the deviance indicates 91.6, that it's actually a decent fitting model, that it fits quite well to the data. And I just did a quick plot to see what that looks like, because I do like visualizations. It sort of helps illustrate, you know, what you're actually seeing. So you can, with this, you can see that the model follows almost kind of the general flow at the start of the cholera infections, and then it gets to about June and goes up. Again, it's sort of fitting a smooth line as it would do, so it doesn't take into account all the kind of lumps and bumps that occur that we saw at the start, and then it comes down at the end. But the overall trend of how an infectious disease tends to work, it sort of captured that, but maybe not as accurately as it could. And it is a very simple model, one predictor. Realistically, there are going to be many other factors that can influence deaths, vaccination rates, age of the population or age structure, poverty is another one, and pregnancy, anything really. So there might be a number of other variables that you need to account for when you're modelling. So I think I was just going to finish there. I have started on the next section, but we can continue with the heftier bits, I think, after the break. So I will stop sharing. Thank you for listening.
Thank you. That was brilliant.